Okay, so this online lecture is meant to go over the idea of electric potential energy and then another quantity called electric potential or voltage. So we've looked at the idea of potential energy with mechanics. We looked at gravitational potential energy. We looked at spring potential energy. And in both of those cases, we were looking at the idea that a force could potentially cause an object to move. So in the case of gravitational potential energy, the gravitational force could potentially cause an object to move. And in the case of spring potential energy, the spring force could potentially cause an object to move. So the same thing is true with electric potential energy. The electrostatic force could potentially cause charges to move. So when we think about how we can look at how a force can translate into energy, we do that through the idea of work, through the lens of work. So we know that work is equal to our change in energy. And we also know that it is equal, so our change in energy, in this case, our change in potential energy, or electric potential energy, can be equal to FD cosine of theta, okay? Now in this case, our force is our electrostatic force, so K Q1, Q2 over R squared. And if I substitute this in over here, I'm going to get delta UE is equal to K Q1, Q2 over R squared. So that's my F value times distance times cosine of theta. Now cosine of theta term. This is going to be looking at, well, what is this force doing? Is this force in the same direction as the distance the object is moving, or is it in the opposite direction that the object is moving? And if we think about this cosine theta term, it's always going to be 1. Because if I have two charged objects, and let's say I've got a positive and a negative, if the force is an attraction force, then my object is going to move that distance. The angle between the force and the distance is 0. Let's say, on the other hand, that I've got two positive charges. The electrostatic force would be in this direction. My distance would be in this direction. Again, the angle between the electrostatic force and the distance is going to be 0. So the electrostatic force is going to cause the object to move in the same direction that force is. So this cosine theta term is just going to become 1. The other thing that we need to note is that the distance that the object moves is going to be the same distance that this r is. This r is the distance between those two objects, and so the object is just going to move further and further away. So one of these r's goes away, and we get a relationship for the electric potential energy between two charged objects is equal to K Q1 Q2 over R. So this is the electric potential energy between two charged objects. And that electric potential energy is either going to cause those two objects to want to come together or to spread further apart. Okay? Now, electric or energy, any type of energy we've measured before has been measured in joules. And when we're talking about charged particles are really, really small. And so the amount of joules they're going to have is very, very, very small and minuscule. And so sometimes it's not really realistic to think about the total amount of energy in the system because it's such a small, small value. So we have another quantity called electric potential difference. It has a few AKAs. Sometimes we call it just the electric potential. Sometimes we call it potential. Sometimes we call it potential difference. It's all going to be describing the same thing, and what that is this is the amount of electric potential energy per charge in a system. Sloppy, sorry guys. This is the amount of electric potential energy. That's still sloppy. Third time's a charm. Electric potential energy per charge. Its symbol is a capital V, and oftentimes you'll see me like make the big V with little caps on so that you know there's a difference between this and velocity. Okay. Because another name for this is voltage, because that's the unit for it. So the symbol is a capital V, and if I think about the equation for this is it's the amount of electric potential energy. So it is looking at what is our potential energy in our system divided by Q. Okay. Sometimes we see this rearranged to be like the potential energy is equal to QV, okay, as well. Same thing. And the units for this are voltage, volts. And we abbreviate that as capital V. So the amount of electric potential per charge depends on the amount of electric potential energy in my system, and it also depends on how many charges are in my system. And we can quantify this even more with, let me bring this over here. I'm actually going to change my on here. If my equation for electric potential or my equation for voltage, again, same name, there's a lot of AKAs, is my amount of potential energy per Q. If I think back to the equation for electric potential energy that we just derived, this is K Q1 Q2 over Q, lies over R, and then divide that whole thing by Q, you can see one of my Q's goes away, and so my resulting equation for electric potential is KQ over R, okay? And so this is the potential an object has, or a charged object has, to affect another charged object. Okay, so this is the potential a charged object has to affect or influence charged object. I'm going to leave myself room, huh? And you could figure out, if I have a whole bunch of charges, you could figure out what is the total potential in that region of all these charges to affect another charge. Now, something to note is that this is one of the few times when you are calculating electric potential, you do include the sign of the charge. Because if we're trying to find the net potential in a region, and I have a positive charge and I have a positive charge together, they will work together to influence a third charge to repel it. But if I have a positive charge and a negative charge, they will cancel each other out. And so the negative, like the positive with our Q here and the negative with our Q here would cause that relationship to cancel out so that we wouldn't have that effect. Okay? So electric potential is this idea of how can a charged object potentially influence another charge if I place it there. So it's by itself. By itself, a charged object can have the potential to influence somebody else. It's not influencing somebody else right now, but it has the potential to influence somebody else. And we also can think about that in terms of electric field, because a charged object can influence another object by its electric field, right? So electric potential is just another way of thinking about how a charged object can affect another charged object. So we can also think about the fact that electric potential, so another way to think about electric potential is an object's electric field times the distance from that electric field. Okay? So another way to think about, let me write this better. I'm going to write the equation first and stop talking. Okay, this is the electric potential of an object depends on the object's electric field how far away from that object the electric field is. So it's just another way of essentially measuring how much of an influence a charged object can be. So recall the idea of electric field. Okay? If I have a positive charge, it has an electric field that spreads out from it. Remember, positive charges have electric fields that go outwards from them. And so every charged object has an electric field, and if I were to put I dropped the light markers. If I were to put a charged object right here, this charged object would move because of this guy's electric field. Another way we can think about how this object would move, because there is at this point right here, at this point in space, there is a particular electric field value at that point in space. And another way we could think about that is, instead of thinking about it as an electric field, even the color, my glue is on the floor, we could think about what is the electric potential at that point in space. Okay? So they are both associated with the charged object. They're just different ways of representing how big of an influencer this charged object is. Am I thinking about it in terms of its electric field, or am I thinking about it in terms of its electric potential? And the reason why we have these two different terms, we'll say, to describe how influential the charge is because it's a lot easier to think about the force that will be exerted via the electric field, and it's a lot easier to think about the amount of energy that is potentially there due to the electric potential, okay? Because electrostatic force can be related to the electric field, but the amount of energy can be related to the electric potential. So both of these quantities are related to this charged object. One has the ability to influence the force, and one has the ability to influence the amount of energy associated at that point. Okay? So they're just two different lenses, two different ways of describing properties about this charged object. Okay? And when we get back into class, we will talk about kind of the negative nature in this equation in terms of how it's changing, whether you have a larger, what happens to the electric potential and how it grows. And we will look at just the comparison between all these equations that have K's and Q's and R's, and kind of what the difference is between when can an object have a force versus when can an object have energy, etc. Okay? So the next video is going to be examples of just going through examples with mathematically of electric potential energy, electric potential, and then how that electric potential can cause objects to move and have energy and velocity, etc. Okay?